Hey MathHL. So in this video, we're going to talk about some basics about vectors. So the first thing we have to do is talk about what a directed line segment is. So a directed line segment is just a line segment with direction. So you remember in geometry how you would make a line segment and there would be a point at each end. Well, actually now we're going to draw it so that it has an arrow at one end. However, this arrow does not indicate that it keeps going forever. This simply indicates the direction of movement. So it is only this long, but it's moving in this direction as opposed to this direction. So that's a directed line segment. Well, a vector is a collection of equivalent directed line segments. So for example, a vector, this is the same vector as that, which is the same vector as this, which is the same vector as this. They all have the same motion and length. So these vectors are all the same vector. We could maybe call it vector u. Sometimes we use lowercase letters to label vectors. U is a common one. So because all of these have the same direction and length, they are considered the same vector as each other. This one's a little bit off, but you get the idea. So a vector does not hold a specific place in space. It's just simply the combination of a length and a direction. But it's all of the ones that do that. So moving on, let's take a look at what if we wanted to make a new vector with a linear combination of existing vectors. So they've labeled this one vector A and this one vector B. There are two ways to label vectors. One way of labeling a vector is with a bold letter, as you see here and here. This is also an attempt at making a bold letter, though it doesn't appear very bold. The other way to label a vector is by putting this little arrow on top. That's when you're unable to make it bold. You'll see that later on in our unit. So two ways to label a vector. So I could call this one vector A and make it bold, or I could call it vector A. Either one of those things would be fine. Okay, well, how do I draw a vector that is 3A plus 2B? Firstly, you just pick a place to start, because remember, a vector doesn't have a specific location. So I just picked the bottom corner, and now I'm going to attach three of these together, end to end. So there's 1, 2, and 3. And now, onto the end of this, I have to attach 2 of the B's. Well, the B looks like it goes 3 units to the right, so I need 2 of those. So now I have the beginning of the sequence and then the end. My vector is not what I've drawn so far. My new vector, 3A plus 2B, is to connect the first point where you started along with the last point where you ended. And I'm going to use a ruler so that that's nice and straight. So what you see in orange is vector 3A plus 2B. So that's how you make a vector in geometric space. So for this next one, I'm going to pick a starting point here. I want half of A. So I only want to go half of vector A, which would bring me right here. And then I want to go 2/3 of vector B, but as you can see, it's minus, which means instead of going to the right, as the direction indicates, I want to go to the left. So 2/3 of this would be 2 units, but I want to go to the left. So my vector would be this right here. That vector is 1/2 A minus 2/3 B. Very small little vector in there. By the way, there are some names that we can use when we refer to these things. The point where your vector begins is called the initial point. The point where your vector ends is called the terminal point. Okay, so we've looked at vectors in 2 dimensions. Let's now look at vectors in 3 dimensions. So they've given you this rectangular prism that's slanted. I believe you pronounce this paraplelepid, but I could be wrong on that. But it's basically a slanted rectangular prism, is what we would call them. But it's not a rectangle because it's slanted. So it's like a parallelogram prism. So that's what this is here. Notice that there are three vectors that are defined on this. Vector A starts at point A and goes to point B. Vector B starts at point A and goes to point D. And vector C starts at point A and ends at point E. However, there are a number of other vectors. No, they're not other vectors. Vector C appears in other places too. For example, this is also vector C. It has the same direction and the same distance. So that would be an equivalent vector, vector C. This would also be vector C. This would also be vector C. So there are four of each of these vectors in this paraplelepiped. So what we want to do is we want to write how you would get from F to D, but using only a combination of A's, B's, and C's. So when they give you a vector with 2 points listed here, what they want is the initial point to be F and the terminal point to be D. When we're interpreting this of like how do we do the work, we basically start at F and ask ourselves, how would I need to move along the sides of the paraplelepiped to get from F to D? Well, here's F and here's D. So one direction I would have to go is I could make my way there by going this way, and then this way, and then down. And you're like, but there are other ways you could get there too. Yes, there are. They will all simplify the same way. So let's track this system of movements here. So from F to G would be the same as from A to D. So that's vector B. From G to H is the same as vector A, but going backwards. So I'd be minus A. And then from H to D is the same as vector C, but again going backwards. So that would be negative C. No matter which order you went, though, you'd have a negative A, a positive B, and a negative C. And the order doesn't matter on this. So part B of this question is asking us to figure out how we would get from M to A, or in other words, what is vector MA, but written only with A, B, and C. So same basic idea. I'm going to start at M and end at A and figure out how I'd get there. M is the midpoint of CG. So I basically know I'm going to use half of C. So I can go down this way and then forward toward B and then to the left toward A. That'll get me where I need to go. So this little portion right here is C, but it's backwards and it's only half. So I'm going to put negative 1/2 C. Notice I'm not writing my letters bold, so I'm putting a little arrow on top to indicate that it's a vector. Okay, so now we're here. Now we need to move forward, which is the same as vector B, but again backwards. So we'll have minus vector B. And then now we're here, so we need to get to A. So we're going along the same vector as A, but we're going backwards again, so negative A. It might be more visually appealing to write our vector alphabetically, so feel free to do that if you want. Also, it might be more visual appealing to not have a negative on each one, so I just factored the negative out. But technically, either of those representations would be true. Okay, let's talk about some laws regarding vectors. The first one we're going to talk about are parallel vectors. Parallel vectors are vectors that have the same direction or the opposite direction. Those are also considered parallel. I'll describe it numerically as well, but let's say we have vector A here, and we have another vector that's twice as long as that, but it's going in the same direction, like 2A, for example. these would be considered parallel vectors. A would be parallel to 2A. You're like, wouldn't A always be parallel to 2A? Yes, it would. But let's say that we gave it a different name. Like, let's say we gave it the name B. Instead of calling this other one vector B, or vector 2A, what if we called it vector B? We could then say vector A is parallel to vector B. Because they have the same direction, they do not necessarily have to have the same magnitude. So basically, if you can get the magnitude of one of them by just timesing by a number, that is considered parallel. So vector B is some scalar, let's call it k, times vector A. In this example, it's exactly 2. K is 2, because B is twice as long as A. Okay, opposite vectors. We've already discussed this a bit in the prior examples. Opposite vectors would be written, let's say I had vector AB. An opposite vector to that would be vector BA. So we could consider AB to be the same as negative BA. It's just going in the reverse direction. So if you put a negative in front of one, now they're the same. What about a zero vector? Yeah, real exciting, right? A zero vector. A zero vector is when you're starting and ending at the same point. Nothing's happened. You're starting at A, you're ending at A, so it's just zero. We've talked about addition and subtraction when we've graphed or used a diagram to talk about vectors. Well, as it turns out, if you look at the addition of vectors, it is commutative. So for example, that should not be plural, it should be singular. Addition of vectors. So if you tried to draw A plus B, you would get the same final result as if you did B plus A. So addition of vectors is commutative. It's also associative as well. So associative is when you do them in different orders. Sorry, when you group them differently. So if you group vector A and B together first, and then add that to vector C, that's going to give you the same result as if you group B and C first, and then add A plus that resulting vector. So it doesn't matter basically what order you add vectors in. Vector addition is commutative. Okay, let's talk a little bit more about addition of vectors. We're going to talk about a couple of rules, or a couple of laws, rules, laws, same difference. First, we're going to talk about parallelogram law. And the reason that it's called the parallelogram law is because the diagram showing it is a parallelogram. So what it's saying is that if you want the resulting vector AC, if you want to start at A and end at C, then you're going to have to travel along AD, or sorry, I looked at the wrong order, but it's commutative, so who cares? We're going to have to add AD with AB. And you're like, wait, but that's DC. But tell me something true about DC and AB. They're equivalent, right? So since DC and AB are equivalent, we can use them in replacement of one another, in substitution for one another. So AD plus AB, the two sides of the vector that come from A, automatically will result in AC. You could also phrase this a little differently. You could have said AD plus DC equals AC, or AB plus BC equals AC. But the parallelogram law in and of itself, those are kind of results of that. The parallelogram law in and of itself say that the two vectors coming from the same vertex added together will give you the diagonal of that parallelogram. The triangle law. The triangle law we've actually already used. Let's say that this is vector AB. You'll notice that now I'm using, instead of a lowercase letter, I'm using the terminal and initial points to represent the vector. We use this a lot when we're doing geometry problems with vectors because it's important to know where we're starting and ending. So let's say I wanted to add vector AB, and I had another vector BC, and that vector looked like that. And let's say that I added those together, vector AB plus vector BC. That will result always in vector AC. We actually used that when we did the examples on the front page, right there. The reason we're talking about some of these laws, or rules if you prefer, is because we're going to use them in the next lesson to actually work out some problems. But for now, we're just talking about what they are, the fundamental stuff. Okay, now that we've looked at a little bit of the geometry of vectors, we're going to talk about how you can write them. We've already discussed a couple of ways that you can write vectors, but we're going to discuss a couple more right now. So let's say that I had a vector A, and I wanted to describe how the vector moved. Let's say it was like this. Let's say this was vector A. And I want to describe how vector A is moving by thinking about how it's moving horizontally and how it's moving vertically. Maybe it's moving horizontally 5 units, and it's moving vertically 4 units. Well, there are a few ways that we can write that vector out in that way. We call that component form. We're breaking it down into its components. One of them is to write this, 5i plus 4j. I is what we call a unit vector in the x direction. J is a unit vector in the y direction. When we say unit something, we mean 1 unit. So it is a vector of direction of 1 unit in the x direction. J is a vector of 1 unit in the y direction. So for example, if I was to graph these, and this was 1 and 1, this would be I, this would be J. So you can use those in combination with scalars to write out what your vector is. Okay, sorry for that interruption. So that's one way that you can write out a vector in component form. Another way that you can write out a vector in component form is by writing it as a vertical matrix. So this would be 5, 4. And this is just a way that you can illustrate it's moving 5 units to the right and 4 units up. Another way that's used less frequently in IB, but you do occasionally see it, are with these triangular brackets. And the first number is the x movement and the second number is the y. So 5, 4. All of those represent this vector A right here. Okay, so those are 3 different ways that you can write vectors out. We're going to use all 3 of those at different points in this unit. There's a little box with some information here, and all that this is saying is that if you have a vector A would be written with some scalar times I, like 5i, for example, and some scalar times j, so 4j, and maybe there's another number in front, like a 2 or something. You can just take that 2 and multiply it in. So if I did that with this one, if I wanted 2a would just be 10i plus 8j. So that's what that is illustrating there. Written in column vector form, you would just multiply the 2 times each component. Again, you'd have a 10 and an 8, a 10 and an 8 if the lambda was 2. Okay, the reason that they illustrate that is because of what we're going to do next. We are going to algebraically find some vectors. So for part A, we're being asked to combine vectors A and B together. So we'll have 3i minus 2j plus negative I plus 4j. You simply treat this as though you're adding like terms. That's it. So you're going to get 3i and negative I would be 2i, and negative 2j plus 4j would be 2j. So that would be your resultant vector if you added together A and B. Basically, this is just doing a shortcut. Instead of drawing it all out like we did here, you can find what it would be by simply using algebra. Let's skip a couple of these. Let's try D. 5a plus 4b. So I have a scalar 5 that I'm going to multiply times vector A, and a scalar 4 that I'm going to multiply times vector B. So I'll end up with 15i minus 10j minus 4i plus 16j. And now I can collect like terms. So I'm going to end up with 11i plus 6j. That would be the resultant vector in that case. Okay, next little topic, just a couple more and then we're done with this first video. Linear combination of vectors. So what we're talking about here is when we want to combine vectors together in a specific way, the first thing we're going to do is we're going to say let vector A be a1i plus a2j. And we're going to let vector B be b1i plus b2j. And what we are trying to do is make a general sort of statement instead of a specific statement like this one here. So when we are doing a linear combination of vector A and vector B, so maybe we have some number times A, let's call that number lambda, and some other number times B, let's call that number mu. When we want to do a linear combination, we're just saying that we want some number times a vector plus some other number times a vector, and we want to know what happens. So if we were going to write this out, we would have lambda a1 I plus lambda a2 j. And then here we'd have mu b1 I plus mu b2 j. So I'm just multiplying the mu and the lambda times my original vectors. And then what will happen is that we want to group them by like terms. We think of the i's as being like terms and the j's as being like terms. So these two would be like terms. And if I wanted to factor out the I would get lambda a1 plus mu b2, and then the I. If I wanted to group together the two j components, I would get lambda a2 plus mu b2. Plus mu b2 j. I typoed earlier. This should be b1 back here. I made a typo. We were combining this term here with this term here. See how it has an a1 and a b1. I just typoed, no big deal. Okay, so that is how we can combine to get a linear combination of something. We're just multiplying the lambda and the mu in, and then basically adding like terms. Now, why would I do all that work when this was not that hard? Like, why do this when I can just like do the specific case? Well, what if we wanted to go backwards? This is where it can get a little tricky. I want to express this new vector as some linear combination of these two vectors. So I want 4i minus 7j to be some scalar times vector A plus some other scalar times vector B. And so now what we need to do is figure out how we can do that. What scalars would I need to use for each of these vectors to get the result I need? That's what we're figuring out here. So what would the number in front of the A have to be? And what would the number in front of the B have to be so that I have some A plus some B that when you put them together make C? That's what we're figuring out. What would lambda and mu be so that that can happen? Well, what we can do is we can start multiplying some stuff out, and grouping things together by i's and j's. Remember how when we worked on complex number stuff, we grouped together the real part and the imaginary? Same idea here. We're going to group the I parts together and the j parts together. So we'll have 4i minus 7j equals negative lambda I plus lambda j plus 2 mu I minus 3 mu j. So now we've got these I parts, and logically speaking, the I part on the left needs to equal the I part on the right. So then 4i should be equal to negative lambda I plus 2 mu I. And now we can group the j parts together as well. Oops. The j parts together. So we'll have negative 7j equals lambda j minus 2 mu j. And so now we can cancel out all the j's, and we have 4 equals negative lambda plus 2 mu. And over here we have negative 7 equals lambda minus 3 mu. So now we can solve these as a system. I can stack these up. I'll get 11. Oop, that's a negative 7, my bad. So negative 3 equals, the lambdas cancel, negative mu. So 3 equals mu. Plug that back in to get lambda. So negative 7 equals lambda minus 9. Add that over, and we get that lambda is 2. So that means that we would need to have the linear combination to get C. We would need to have 2 of vector A plus 3 of vector B in order to come up with C. That is what we're looking to do there. Okay, that wraps up this first video. More to come.